My name's Andrew Hamilton. I'm the Vice-Chancellor of Oxford University. It is an enormous pleasure to welcome you all to this Oxford Martin School lecture, to see the Sheldonian packed to the rafters for a very distinguished guest. It's an enormous pleasure for us to welcome Elon Musk, who will be talking about the future of energy and transport. This is a lecture in the series of the Oxford Martin School. The Oxford Martin School, as all of you know, is a very dynamic, a very important interdisciplinary research school here in Oxford, focused on many of the challenges of the 21st century, and of course one of them is transport. And so to hear from Elon Musk today very much fits in with the priority of the Martin School. It's my pleasure now to introduce the director of the Martin School, Professor Ian Goldin. Ian has been director since September 2006. He is a South African. You'll hear in a few moments there's a South African Lincoln connection tonight, which we're all very pleased and proud of. Ian came to the Martin School, as I said, 6 years ago from the World Bank, where he was vice president, and prior to that he was director of the development policy of the World Bank. So it's a pleasure, Ian, to introduce our speaker this evening.
Thank you very much, Vice-Chancellor. Welcome, Elon. It's an enormous pleasure to bring great minds together, and that's why my job as director of the Oxford Martin School is so fun. And meaningful because we are dealing with the greatest challenges of the 21st century. In Elon Musk, we have someone who is focusing on two key areas, transport and energy. He's an extraordinary intellect, but he combines his science with the business acumen and a commitment to society which is unusual. It's the combination of not only business, but also with science and knowing what to apply it for that makes him a really special visitor tonight. An extraordinary talent with the right commitment to deal with the challenges of the 21st century. He's the engineer and entrepreneur who builds and operates companies to solve global environmental, economic, and social challenges. He's the CEO and chief designer of Tesla Motors, you'll see the car outside, and CEO and chief technology officer of SpaceX. At SpaceX, Elon is the chief designer and has overseen the development of the rockets, which have taken it now twice to the space station. They've received the $1.6 billion NASA contract to provide commercial replacement for the cargo, and as he will tell us, no doubt, they have now got a commitment as well to take astronauts. It's the most extraordinary thing visiting the factory, as I was privileged to do, and to see not only the energy and commitment of Elon and his team, but also the originality, just how much of what they are doing is original, how much they are taking away. It has taken governments before. 4 governments have achieved what Elon has achieved. Never before has a private individual done so much, so quickly for space. In addition to his work on SpaceX, as if that wasn't enough, his work at Tesla is developing a car which has now won this year the automobile and the Auto Trends Automobile of the Year. Now, for those of us that don't follow cars, this is the equivalent of winning the the Grammys and the Oscars in the same year, or for us academics, 2 Nobel Prizes. It is an achievement which is quite remarkable, and having driven, he was kind enough to trust his Roadster to me. Having driven one of his cars, I felt like I was in a space rocket. It had this G-force, which I've never before experienced. This car, I believe, will revolutionize transport because it will enable people to see that you can do things without carbon, which were unimaginable before. In addition to this, he started and runs Solar City, which is developing and now the biggest producer of solar power systems in the US. He began at PayPal, which he co-founded, and all of you will know about PayPal. He became its CEO, and then moved on to these other things. The Vice-Chancellor mentioned that we have a South African connection. We went to the same high school, and we both escaped. He went from there to do his degrees at Pennsylvania and at Wharton, and in many ways has moved on from that. But the work that he was doing, including on supercapacitors, has continued to drive a lot of what he does today. It is this incredible combination of vision, bravery, and ability which has had him likened by many to a 21st century version of what Brunel was in the 19th century and Henry Ford in the 20th century. I have no doubt that he will benefit us in ways that we still do not imagine. He exemplifies the ambition of the Oxford Martin School and its interest in solving the problems of the 21st century, and it's a huge pleasure to invite him to address us.
Thank you very much for the kind introduction. It's an honor to be here. This is an incredibly beautiful theater, and it's amazing to be in a place designed by Christopher Wren. And speaking of Brunel, actually, I'm a big fan of Brunel, and I have 5 boys, and I really wanted to name one of them Brunel, or Eisenbart. I like them. No luck. Hopefully one in the future. So I guess I'll just tell you the kind of the story of kind of how I came to be here, or the various things that I did, and maybe why I did them, and hopefully that's a bit helpful. And then we're going to have quite a long question and answer session. So I look forward to feel free to ask me any question, no matter how provocative or challenge what we're doing. I'm actually always interested in negative feedback, actually. So the way I started out was I did start out in South Africa. Went to Pretoria Boys High, and then left actually by myself initially to go to Canada, and then the US to college. And graduating from undergrad, I had to sort of make a decision, and one path would have sort of led to Wall Street and I guess quite a big salary, and then the other was to do grad studies and try to figure out a technical problem. And I didn't much like the first one, so I decided to go out to Silicon Valley and go to Stanford and try to work on ultracapacitors for use in electric vehicles. And I do actually think there's potential for a significant breakthrough in that area, and actually to have an energy storage mechanism that's better than batteries. It's not necessary for transport to go electric, but I think it's something that would accelerate that. So I was sort of about to get into grad studies, and then the internet. It was clear that the internet was going to be something that would be very important to the future. So I thought, well, I could either sort of spend 5 years in a graduate program and discover that the answer is that there is no way to make a capacitor work, and perhaps get some nice papers published and that kind of thing, but that would be the most unfortunate situation, I thought, because you can come to one of the possible things is to determine that success is not one of the possible outcomes. I couldn't actually bracket the uncertainty on that. So I thought I can either do that, or I can work on building elements of the internet. And this was in '95, so nobody had actually made any money on the internet. So but I thought the internet would be something that would fundamentally change the nature of humanity, where it was like humanity gaining a nervous system, where all of a sudden any part of humanity would know what the collective would have access to the collective knowledge, and that's true. It's really quite a remarkable transformation. In the past, you'd have to, and if you wanted access to a lot of information, you had to be near a big library or something, like the Great Bodleian Library nearby. And then that would be the only way to gain access to information. And now with the internet, with everything online, you could be somewhere in the jungles of South America, and if you've got access to an internet connection, you have access to essentially all the world's information, with a tremendous amount of analytical power behind that. So I think it literally has gone from a situation where people would communicate almost like via osmosis. If you can imagine sort of a creature, a simple multicellular creature that would communicate via quite slow chemical signals. And now any part of humanity knows what every other part of humanity does immediately. It's pretty incredible. So anyway, I wanted to be part of building that, so I decided to do a couple of internet companies, and that actually worked out reasonably well. The first one helped bring the media companies online, and then we sold that, and then started another company which you may have used called PayPal, and that we sold for actually a larger sum of money to eBay, and that left me in the fortunate position of having the capital to pursue the two other things that I thought would most affect the future of humanity, being sustainable energy, both the production and consumption of energy in a sustainable manner, which I think is arguably the most pressing problem of the 21st century, and then the other one, which is the extension of life beyond Earth. The one I did first was the space company, and the genesis of that is kind of interesting, because at first I didn't think that it would be possible to create a rocket company, and I thought what would really make a difference is to have a mission to Mars, a small sort of send a small payload to the surface of Mars, that would get the public excited about to reignite the passion for space exploration, such that we could go beyond what we did with the Apollo program. And I thought it was quite sad that the Apollo program represented the high watermark of human space exploration, it was not something that I was able to witness in real time, because I was -2 when they landed. It just seemed as though that if I thought about the future, one where we were a true spacefaring civilization out there exploring the stars and making the things real that we read in science fiction books and movies, that seems like a really exciting future that sort of made me feel good about the future, and one where we're forever confined to Earth made me feel a bit sad. So that's really what I was trying to figure out, is how do we reverse that? And then, like I said, at first I didn't think it would be possible to create a space company, because it seemed like the province of governments. But so my first thought was, well, let's see if we can do a philanthropic mission to Mars, and get the public excited about the idea of going there, and then that would lead to an increased budget for NASA, and then we could go there. That would hopefully work. So I figured out how to compress the cost of the spacecraft and the communication systems and the payload and so forth, and then it would have been a small greenhouse about 1 meter across, with seeds and dehydrated nutrient gel that would land. You'd hydrate the gel upon landing, and you'd have this great shot of green plants against a red background. In the US, that's called the money shot. The public tends to respond to precedents and superlatives. So this would be the first life on another planet, the furthest that life's ever traveled. And I thought, okay, well, that would get people pretty excited, and maybe they could envision people being there. And we'd certainly be able to figure out a lot of engineering and scientific data about what it took to maintain plant life on the surface of Mars. So I got through most of that, and the thing I got hung up on was the rocket. so getting there in the first place. And there were the US options from Boeing and Lockheed were simply too expensive. I couldn't afford them. And so I went to Russia 3 times to negotiate purchasing an ICBM. Of course, I mean, desperate times call for desperate measures. So, I went there. So I did 3 visits there, and at the end of it, I was able to get to negotiate a price actually. To buy 3 of these things, 3 of the largest ICBMs in the Russian fleet, but they were still pretty expensive, and by the 3rd trip, I actually came to the conclusion that I was operating under the wrong premise, that I was actually mistaken about the willingness to send people to Mars to expand the space frontier, and it actually. In retrospect, it was quite silly of me to think that people were not interested in such a thing, or had lost the will to do this. In fact, people had really thought that it's not possible, or not possible for an amount of money that wouldn't materially affect their standard of living. So I came to the conclusion that even if we succeeded in doing this mission, that wouldn't be enough. That would perhaps add a little bit more to the will to do it, but it wouldn't make it clear to people that there was a way. And this is a case of sort of almost the opposite. I think if you can show people that there is a way, then there is plenty of will. So after that 3rd trip, I'd learned a lot more about rockets at that point, and I held a series of meetings, just sort of brainstorming sessions with people from the space industry to try to understand if I was missing something fundamental about the ability to improve rocketry. And this is where I think it's helpful to use the approach, the analytical approach in physics, which is to try to boil things down to first principles and reason from there, as opposed to reasoning by analogy. And the way this applied to rocketry was to say, okay, well, what are the materials that go into a rocket? How much does each material constituent weigh? What's the cost of that raw material? And that's going to set some floor as to the cost of the rocket. And that actually turns out to be a relatively small number. Certainly well under 5% of the cost of a rocket, and in some cases closer to 1 or 2%. And so I call it sort of maybe the magic wand number. So if you had a pile of the raw material, piles of raw materials on the floor, and you could just wave a magic wand and rearrange them, then that would be the best case scenario for a rocket. And so I was able to see, okay, well, there's clearly a great deal of room for improvement, even if you consider rockets to be expendable. And so I think that's what I mean by sort of thinking about things from a first principle standpoint. If on the other hand, I sort of analyzed it by analogy and said, okay, well, analogy would be, well, what are all other rocket companies, what do their rockets cost? What historically have other rockets cost? And that would be sort of an analogy thing, but it really doesn't illustrate what the true potential is. And so I think it's sort of a first principles approach is a good way to understand what new things are possible. So this is a good framework. And it doesn't mean you'll be successful, but at least you can determine if success is one of the possibilities. That is important, I think. So started SpaceX, and initially had decided to make a small rocket called the Falcon 1 that was capable of putting about half a ton into orbit. And this did not go smoothly. I just want to. And it was quite difficult to attract the key technical talent, and of course I was quite ignorant of many things, made lots of mistakes along the way. And the first 3 flights of the Falcon 1 failed, or rather, they certainly didn't get to orbit. The second and third flights arguably got to space, but they did not reach full orbital velocity. And then fortunately, the fourth flight worked. And if it hadn't, SpaceX wouldn't be around, because I'd basically run out of money. So that was a bit of a nail biter. And thank goodness. And in fact, this all happened in 2008. So yeah, there was really no ability to raise outside money in a meaningful way in 2008 because of the financial crisis. So you can imagine trying to go to raise money, saying, well, yes, we just had 4 failures and the world is in financial ruin, but would you like to give us some money? That would be a definite no. So fortunately, that succeeded, and we were able to go from Falcon 1 to begin designing the Falcon 9, which is an order of magnitude larger vehicle, and in fact has more than 20 times the payload. So it's got a payload to orbit of over 10 tons, and that actually has gone a lot better because we had the experience of Falcon 1 to go by, and part of the reason we started with Falcon 1 was because I thought we would make a lot of mistakes, and if we're going to make a lot of mistakes, then it's best to make those mistakes at a small scale rather than at a large scale. And that seems to have worked, because going to Falcon 9, we've had 4 flights of Falcon 9, and they've all 4 of them have been successful. So I think that principle seems to have worked reasonably well. You know, touch wood and all that. Flight 5 is coming up soon. And then we also developed the Dragon spacecraft because somewhat opportunistically, NASA announced that they were going to retire the space shuttle, and they didn't have the budget to develop a cargo transport capability to the space station via the normal large government way, and so they put it out to bid to commercial industry for the first time in NASA history. It was quite a big step, and we were lucky enough to win one of those contracts, and then the other company wasn't able to execute, and so they got cut, and so we ended up being the primary means of transporting cargo to and from the space station. So we just did the first 2 missions, the first 2 space station resupply missions this year, and thankfully both of those worked. And then going from there, NASA then said, well, what about astronaut transport? And so they put out a big competition and awarded 2 contracts for astronaut transport, one of which went to Boeing. They got a slightly larger contract, and then one to us. And so hopefully in about 3 years, we will have Dragon version 2 and the next generation Falcon 9 rockets transporting astronauts to and from the space station. Then we've got Falcon Heavy, which is about 3 times the capability of Falcon 9, and that will hopefully launch in about a year or 2. That'll actually be the most powerful rocket in the world by a factor of 2. So we're making sort of steady progress. The Falcon Heavy, to put that into perspective, has about 60% of the capability of the Saturn V moon rocket. So if you were to combine 2 flights of Falcon Heavy with orbital rendezvous and docking, you could actually send people back to the surface of the moon. So I think now we're really sort of talking about, you know, advancing the frontier, which I think is quite important. And then the really major breakthrough that's needed in rocketry, the pivotal one, which we're aspiring to make, is to have a fully and rapidly reusable rocket. This has not been achieved before. The space shuttle was an attempt to achieve that, but it was not a successful attempt, unfortunately. The main tank of the space shuttle was thrown away every time, which was also the primary ascent aeroframe. And even the parts that were reusable were so difficult to reuse for the space shuttle that it ended up costing 4 times more than an expendable rocket of equivalent payload capability. It was the right goal, but didn't hit the target. And I think this is actually incredibly important. I think it may not be completely intuitive, but I think perhaps if one refers to other modes of transport, it makes more sense. Because all other modes of transport are fully and rapidly reusable. And that applies to a bicycle, a horse, plane, ships. In fact, in sort of normal life, it would be quite silly to discard your horse after every ride, or dump the plane after you flew it. The cost of a 747 is about $300 million, and you'd need 2 of those to do a round trip from Los Angeles to London. But I don't think anyone has paid $500 million to do that. So, and nor would one want to. I mean, there'd be a lot of travel by boat and train and that sort of thing if that was the true cost. So it's extremely important in rocketry to achieve full and rapid reusability. This is not an easy thing to do because of Earth's gravity well and just the basic physics of things. So there have been many attempts to create a reusable rocket, but they've generally, they've all sort of been cancelled along the way once people realized that they would not succeed. In fact, usually they got cancelled quite some time after it was obvious they wouldn't succeed. But the essence of the problem is that if you design an expendable rocket and do quite a good job of it, you'll get 2 to 3% of your liftoff mass to orbit. Then if you say, well, how much mass is needed to return that rocket and be able to fly it again quickly? Well, about 2 to 3%. So you can basically get nothing to orbit, is the way it's been in the past. So in order to do something useful, what you have to figure out is how do you get a much larger percentage to orbit, let's say ideally on the order of 4% of your liftoff mass to orbit in an expendable configuration, and then compress the reusable elements down to about 2%, so you have a net payload to orbit of 2%, and then you could really have something that's quite useful. And the cost of the propellant is only about, let's say, 0.3% of the cost of the vehicle. If you take Falcon 9, for example, which uses quite expensive fuel, relatively speaking. I think there are lower cost options. The cost of refueling or reloading propellant on Falcon 9 is about $200,000, and the cost of the rocket is $60 million. So it's just like a plane. I mean, it's just, if you were to refuel a plane, not very expensive. If you want to buy a new plane, very expensive. At this point, I'm really reasonably confident that it can be done, and now it's a question of executing to make that design work, and seeing if there are any gotchas. And there'll probably be a few craters along the way, so I'm not expecting this to be a smooth journey. As long as the rocket doesn't land on anyone, it'll be fine. So that's really what SpaceX is focused on right now, is kind of scaling up the size of the rockets and trying to achieve this full and rapid reusability. So if you're curious, you can just, we're fairly public about things, and you can just follow it on the SpaceX website. So that's what we're doing on the SpaceX side. Then in parallel, we've got Tesla, which is developing electric vehicles, and it's sort of a whole separate storyline. And tell me if I'm going on too long, and stop me at any point. Feel free to leave if it's getting boring. I won't be offended. With Tesla, the goal is to try to create electric vehicles that are more compelling than gasoline vehicles as a product. I mean, the fundamental issue we have in energy and transport is the tragedy of the commons. You know, we've got the CO2 capacity of the oceans and atmosphere that is unpriced, or mostly unpriced. And so it's almost like we're sort of dumping garbage in the atmosphere, and nobody's paying for garbage collection. So it's a most unfortunate situation, because there are quite significant vested interests in oil, gas, and coal, with enormous amounts of money. It's quite a difficult battle to fight, and you can't expect them to simply roll over and commit suicide or something. They will fight it hard, and they have been. And so, unfortunately, it requires fighting hard back and creating products, in the absence of there being a tax on CO2, creating products that don't rely on the relative economics of using hydrocarbon fuels versus electric cars. And so that was our goal from Tesla from the beginning. And I'm really I'm excited to see that we've achieved that goal, actually, with the Model S, which was, as was mentioned, Model S was recently awarded top honors by, it was awarded sort of Car of the Year and Automobile of the Year, and that was against a very difficult field of gasoline cars. And so I'm hopeful this will be seen as a pivotal moment in transport where people finally appreciated that an electric car could be better than a gasoline car. And then going into the future, our goal with Tesla is to keep refining the technology, increasing the scale of production, and make a mass market electric car that almost anyone can afford. That's step 3 on the strategy. So step 1 was a high price, low volume. Step 2, mid price, mid volume. Step 3, low price, high volume. So we're sort of at step 2, and now we want to progress to step 3 as soon as possible. And we did get quite a bit of criticism at Tesla for creating the Roadster, which we did in collaboration with Lotus. And people were complaining, well, why are you making this expensive sports car? And with the implication that we felt there was a shortage of sports cars for rich people, and we're racing to meet that unmet need, you know. So the real reason is that any car that we make at low volume, which is the first version of technology, is going to be expensive. It didn't matter what that car looked like. So we could make something that looked like a very standard, sort of Toyota Corolla or Ford Fusion or something like that, and it would have cost, say, $70,000. But nobody will pay that for what looks like a mid-size economy sedan. They just won't, or very few people would. But people are willing to pay $100,000 for a fast sports car, and so that's why we started off at that level. And then with another big design iteration and an increase in volume, so we had economies of scale, we were able to create the Model S. And then with another order of magnitude increase in volume and another big design revision, that's what will allow us to cut the price in half again. And then Tesla also supplies powertrains to Mercedes and Toyota, and perhaps other will do that for other car companies in an effort to help them accelerate the transition to electric vehicles. So that's Tesla and SpaceX, and I should mention certainly Solar City, because one must generate electricity in a sustainable way as well as consume it in a sustainable way. And people will say, well, what don't electric cars create pollution at the power plant level? It should be noted that for any given source fuel, it is always better to generate the power at the power plant level and then charge electric cars and run them for any given source fuel, because power plants are much more efficient at extracting the energy than internal combustion engines in a car. They're at least twice as efficient, and usually more like 3 times as efficient. So for any given source fuel, it's always, even if the whole world were always going to be powered by hydrocarbons, it would still make sense to do electric cars. But of course, we must find a sustainable means of generating energy as well. And I think that the most likely, or the main candidate for energy generation is actually solar. I think the physics of this was actually rather obvious because the Earth is actually almost entirely solar powered today as it is. It would be a frozen ice ball at, I don't know, 3 or 4 Kelvin if it weren't for the sun. And our entire system of precipitation is powered by the sun. The ecosystem is almost entirely 99.999% powered by the sun, except for some chemotrophs at the bottom of the ocean. That's it's rather obvious that I think one should try to take a little portion of that energy, and it's actually not much, and convert that into electricity for use by society. So I'm quite confident that solar power will be the single largest source of energy, or electrical energy, for humanity in the future. It will be combined with other things, of course, such as hydropower and geothermal, and I actually think nuclear is not a terrible option, as long as you're not located in a place that's susceptible to natural disasters. That's also, I think, defies common sense. But so as long as there aren't huge earthquakes or sort of weather systems that have names coming at you, then I think nuclear can be a sensible option. And there are much safer and better ways of generating nuclear energy, I'm talking fission here, than existed in the past when nuclear reactors first came out. And then at some point in the future, it'd be nice to make fusion work. Of course, that would be quite good. But in the meantime, I think indirect fusion, being solar power, is a good thing to do. And so that's what Solar City is doing. Is really trying to improve the economics of solar power, and they're doing a great job. I don't run the company, so the credit for Solar City really goes to the two key guys who run that company. But they're doing a great job of really accelerating the adoption of solar power in the United States. And hopefully they'll come to the UK as well. So that's about it. So we can go to Q&A.
Thank you so much, Elon, for that. You make it sound so easy. If only a small fraction of us could achieve that in our lifetimes, I think we'd be absolutely delighted. But thank you, too, for agreeing to take questions and answers. I know that's what you really were looking forward to today. So we have a roving mic. We have some time. And please keep your questions clear and concise. To Elon. I'm afraid there's no microphones at the higher level. It's going to be difficult for the people carrying the roving mic to get up to the higher tiers. So if you want to ask a question, come down to this level of the Sheldonian. Who'd like to go first? Lord Rees over here.
Well, amazing talk. Can I be greedy and ask two questions?
Absolutely.
One of the constraints on both your projects is the energy isn't concentrated enough. Batteries can't store energy as densely as liquid fuel, and even liquid fuel isn't dense enough to have an efficient launch into space.
Right.
So I wonder if you could speculate on that. And the second question I wanted to ask is about robotics in the future. I guess even though you can have a driverless car, people still want to drive the Tesla themselves. Yeah. They won't want to leave that to a robot. But do you think that the advance of robots is going to change people's perspective on manned space flight? So energy concentration and the role of robots.
Yeah, absolutely. In fact, the energy density, basically the amount of energy you can store in a given amount of mass or volume, has been a fundamental constraint on electric cars for a while, and then that's paired and correlated to some degree with the cost per kilowatt hour, the cost of storing that energy in a car. Now, with the advent of lithium-ion technology, that I think is really what enabled a compelling car. And lithium-ion batteries continue to improve. It's sort of a roughly, on average, maybe 8 or 9% per year, which, when compounded over several years, ends up being a meaningful improvement. And as I mentioned in my talk, I think even if there was no improvement in no fundamental improvement beyond lithium-ion batteries, I think we could still take all terrestrial, all ground transportation could go electric. We do need a further breakthrough for aircraft where the energy density requirements are at least 2 to 3 times more significant. But even with current generation lithium-ion, I think we could go to mass market with ground vehicles. And in fact, our focus is really more on reducing the cost of the battery pack than improving the energy density. So I think we're actually in a pretty good spot. I actually now am reasonably optimistic that there will be a breakthrough in high energy density capacitors. I mean, it's sort of interesting if you do the sort of do the basic physics on the energy density potential of a capacitor, using naturally occurring materials, it's quite hard to beat lithium-ion batteries. But if you can figure out a way to make sort of unnatural materials, I suppose, that are accurate to the molecular level, then I think you can actually have some fairly significant breakthroughs. And that was actually developed. The ability to do that was developed in the photonics arena, and applying the sort of photonics breakthroughs to capacitor technology is what has the potential for a really big breakthrough there. So I think we may see something on that level, but it isn't totally required for cars. For rockets, well, there's no way to make a rocket electric, that's for sure. Unfortunately, Newton's third law cannot be escaped. I think, maybe, I mean, certainly, there'd have to be a few Nobel Prizes awarded if there was some way to get around it. That would be really, really convenient. But I do think it's possible with a really efficient combustion rocket to achieve the settlement of Mars. I think we probably want to switch to methane. I think it's really methane or hydrogen are kind of the two best choices there, and probably slightly leaning in the direction of methane because it's easier to handle than hydrogen. Methane is just CH4 versus H2, and both can be produced on the surface of Mars, which is important. Yeah. In fact, I should say that I'm quite confident at this point that it is possible to create a self-sustaining civilization on Mars using only a methane or hydrogen-based launch system, and yeah, and it needs to be a fully reusable methane or hydrogen launch system. It can be done, and the key thing I was trying to figure out was, with volume, is it possible to get the cost of moving to Mars down under $500,000, which I think is, I mean, one can argue about the exact threshold, but I think that's about the threshold at which enough people could save up money and move to Mars. Yeah. I mean, that's how America got created, basically. And come back if they want. If they don't like it, of course, you get a free return ticket. There's sometimes a debate about going to Mars one way and whether that makes things easier. And I think for the initial flights, perhaps, but for long term, to get the cost down, you need the spacecraft back. Whether the people come back is irrelevant. But you must have the ship back because those things are expensive. So anyone who wants to return can just jump on. That's. But until a few years ago, I wasn't sure that success was one of the possible outcomes, and now I'm quite sure that success is possible. Of course, there's a long way between possible and making it real, but I believe it is possible.
And robotics.
And then robotics, right? I think one can accomplish a lot with robotics. I do slightly worry about if robotics get too good, what's the point of us? I think either robotics get so good and there's not much point to us, I guess, I don't know, or they're not as good as us, in which case we need to go. And I'd advocate the second. Hopefully the future there's not some sort of AI apocalypse. Yeah.
Great. I'm sure we'll come back to that. If you'd like, yeah, the gentleman over here.
Good evening. Thanks for taking questions. I just had two brief questions, one on Tesla and the second one on SpaceX. I was wondering if you're familiar with the Sabre engine, the hybrid engine, which is, there's a team of hardworking Rolls-Royce engineers working on it in the Oxfordshire cluster at the moment. It's a hybrid engine that breathes air on the way up. Oh. And you talked about it earlier in your talk, that you're specifically looking at reusable space delivery vehicles and rockets. So that was the SpaceX one. And the Tesla one was, what happened to the original Tesla prototype, the Mule 1?
Yeah, well, we still have the original Mule 1 of the Tesla Roadster. Here I should give credit to a small company in Southern California called AC Propulsion that had a vehicle called the T0. So our very first Mule was really taking a Lotus Elise, kind of jamming a AC Propulsion powertrain into it, and then sort of making it drive. We originally thought that, well, it would be. This is another example of making some mistakes, sort of dumb mistakes, but the thought at the beginning of Tesla was to use AC Propulsion's powertrain and Lotus Elise and get to market fast with an electric car. As it turned out, the AC Propulsion powertrain didn't really work very well and was not scalable for production. It had a lot of issues. And so we had to completely redesign the powertrain. And then the Elise, because our car ended up being 50% heavier and had different weight distribution and load points, we invalidated all of the crash structure and had to completely redesign the chassis. And in the end, I think about 7% of the parts were in common with an Elise. So almost nothing. But we actually inherited some of the limitations of an Elise. So.
Okay.
Okay, so and then, but there's a long-winded answer. I'll try to be less long-winded in my answers. But so with respect to air-breathing hybrid stages, I have not seen how the physics of that makes sense. There may be some assumptions that I have that are incorrect, but really for an orbital rocket, you're trying to get out of the atmosphere as soon as possible because the atmosphere is just thick as soup when you're trying to go fast, and it's not helped by the fact that the atmosphere is mostly not oxygen. You know, it's sort of 80% nitrogen. So mostly what you're air breathing is chaff, not wheat. And having a big sort of intake is like having a giant brake. So the braking effect tends to overwhelm the advantage of ingesting 20% oxidizer. So you could just make, say, the boost stage 5 to 10% larger and get rid of all the air-breathing stuff, and you're done. So.
Thanks, Elon. The gentleman down here, I should say that this is being filmed, so if any of you don't want to be filmed, either don't ask a question or else tell the people who are filming up here afterwards that you'd like your questions extracted, but the assumption is that you're happy to be on record.
Good evening. With the new technologies that has made the availability of shale gas really cheap, and with the boom of the US energy sector, do you think there'll be a limitation in the development of sustainable energy in the coming decade because of the new energy boom that US is facing right now?
Yeah, that's a good point. Obviously, new technology and innovation can have a downside, and one of the downsides is the ability to extract far more hydrocarbons than we thought were possible, including, once you start getting into deep methane or deep natural gas, you're actually tapping into things that are not related to dinosaur fossils. Methane is a naturally occurring gas. There are places in the solar system where where the atmosphere is primarily methane. So it does not require organic origin. So if we dig too deep for methane, we're actually going to a level that has never been seen before, not even in the very earliest history of Earth. So that's very dangerous, I think. But that's why I think it's important for electric cars to be able to compete without economics being a factor. But I think it is very dangerous to be extracting vast quantities of hydrocarbons from deep within the Earth and putting them in the atmosphere. Sooner or later, something very bad will happen, and yeah, it's just. I mean, there are a lot of people, particularly in the U.S., who are vehemently against electric cars and sort of sustainable power. It's quite difficult to reason with them, actually. And they'll say, well, some scientists don't think it's a problem. And I'm like, well, okay, you can find some number of people that will disagree with anything. This actually reminds me of the tobacco industry, where for the longest time they were actually complaining that you'd see ads where they claimed tobacco was healthy for you. I mean, hard to believe these days, but and then there were these reports where there seemed to be some correlation between lung cancer and smoking, and they're like, oh, our scientists have conducted experiments and they show there's no relation at all. It's complete nonsense. And so it got to the point where almost any reasonable scientist would say that yes, of course, smoking causes lung cancer and all sorts of other bad things. Not definitively, but it's extremely likely. And yet the tobacco industry would still say, oh, scientists disagree because 1 or 2% of the scientific community didn't feel that way. And that's kind of, and then the public just hears scientists disagree. They don't hear 99% of them think it's stupid. Yeah, so it's definitely a tough thing, and hopefully that transition occurs before it's too late. There's already quite a bit of momentum in the direction of climate change, and accelerating the removal of hydrocarbons from the crust and placing it in the atmosphere is I think, just very unwise. So anyway, that's why I think it's the biggest problem of the 21st century. So.
The gentleman there, yeah.
You're an incredibly successful and very modest man, but my question's about failure.
They're not about modest.
I think we'd all think you're modest. So. My question's about failure. So I was just wondering, what are you trying at the moment, or what do you think you'll attempt in the future that you're not expecting to succeed at?
Well, I think I'm going to stay on electric cars and rockets for a while. Yeah, it was actually never never my intent to run Tesla. I kind of, because running two companies is quite a burden, actually. It's sometimes I run into people who think, oh, if you're CEO of the company, then they sort of imagine themselves, if they were CEO of the company, they would grant themselves lots of vacation and do lots of fun things. And it's like, that doesn't quite work that way. What you actually get is a distillation of the worst things going on in the company. It's like, anyway, so the idea of taking on something more is very frightening. But I mean, possibly at some point in the future, certainly not the near term, there are. I think there's an opportunity to create an electric jet, essentially, and I do think one could create an electric jet that is really exciting. Something that would be supersonic, vertical takeoff and landing, pure electric, and just a big leap forward. I think that's a distinct. I'm quite confident it's doable, provided that there's a rough doubling of the energy density in batteries or capacitors. So, basically around the 500 watt-hours per kilogram level is where it starts to make sense. And then there's, I do think there's the possibility of kind of a fifth mode of transport, which I've talked about, kind of mentioned tangentially, which is like I call kind of the hyperloop, and I'd like to sort of publish something about that maybe in the next month or two, once Tesla's at steady state production, and I want to flesh it out a little bit so that and pre-address some of the rebuttals that people will come up with, rather than just sort of put it out there and then have the rebuttal occur and have an unaddressed rebuttal. But I guess a way to think of it is it's like a cross between a Concorde and a railgun.
Right, well, we look forward to hearing about the gentleman with the blue shirt at the door. Then we'll come this side.
Hi, thanks for a great talk. At the risk of asking for trade secrets, I was just wondering, having built the Falcon rockets, what was the final conclusion of your analysis as to why your rockets were so much less expensive than government projects?
Well, there's not a the full answer is quite complicated, and requires at least some understanding of how rockets work. And but if you divide a rocket into the cost of the engines, the airframe, the electronics, and then the launch operation itself, those are the marginal cost drivers. And then there's the fixed cost of the company, which is which you divide over the number of launches that take place. But just looking at the marginal cost drivers, it means you have to make a significant advancement in engines, significant airframe, electronics, and launch operation. In fact, it would be easy to point out one of those areas, but success in one of those areas would only have a small effect. So let's say you had free engines. Well, that would only reduce the cost of the rocket by probably 30%, the cost of launch by 30%. And so that's not much, that's not a huge breakthrough. Or free electronics or free airframe. You actually have to compress all of them quite a bit. And then, like I said, you have to make them reusable. I can give sort of an example, an illustrative example in the airframe that may be helpful. The normal way that a rocket airframe is constructed is machined isogrid. And that's where you take high-strength aluminum alloy plate and you machine stiffeners into integrally machined stiffeners into the plate. And I apologize, this is going to go a little slightly technical, but imagine you sort of have a plate of metal and you're just cutting triangles out of it. And that's normally how rockets are made. And most of a rocket is propellant tanks. These things have to be sealed. So they have to maintain pressure and everything, and they have to be quite stiff. So that's normally how it's done. Then the approach that we took is rather to build it up. And to start with skin sections and friction stir weld stiffeners into the skin sections. This is a big improvement, because if you machine away the material, you're left with maybe 5% of the original material. So you have a 20-to-1 roughly wastage of material, plus a lot of machining time, and it's very expensive. If you can roll sheet and stir weld the stiffeners in, then your material wastage can be 5%. So it's the inverse, essentially, where you know, instead of having a 20-to-1 ratio, you've got maybe a 1.1 ratio. It's you know, instead of having 95% wastage, it's 5% wastage. It's a huge improvement. And then you can actually improve the mass fraction too, because if you have stir welded stiffeners, you can increase the profile and geometry and improve the geometry of the stiffeners. So you can have something which is, say, 5 centimeters tall, whereas if you machined it from a plate, it would be limited to the thickness of the plate, which may be 2 or 3 centimeters tall. So you actually end up with something which is both more advanced in that it is better mass fraction, but it is also a fraction of the cost. That's one example, but there are many such things.
I saw one of the most amazing 3D printers when I visited you as well.
Oh yeah, that's good for prototyping.
Malcolm McCullough, who runs our Getting Carbon Out of Transport group in the Oxford Martin School.
So Elon, the question I have for you is to say that we can see that our society is going to go through a major change because of the climate issue and the carbon problem that we have. And looking back in our history, South Africa went through a major change. One of the key enablers to that was the scenario work with Clem Sutton, where they had the high road and the low road scenario. And that enabled people to envisage what would be a good outcome and what would be a bad outcome.
Right.
What is your good outcome with the climate change challenge? How would you envisage what a good world would look like with this climate change challenge?
Well, I think the thing we need to do is the best thing to do to achieve that would be a carbon tax. So I think if we were to just, the market system will work extremely well if it has the right information to work. So if we just apply a tax to carbon and then dial that up according to whatever achieves the target maximum carbon proportion in the atmosphere, that's I think the right way to go. And countries really need to act unilaterally. People can't have this thing, well, you know, if such and such country isn't doing it, I'm not doing it. Well, okay, set a good example, you know, and hopefully over time other countries will fall in line or get ostracized. So I think that's probably the smart move, and then we can avoid there's no need for subsidies and special incentives, which are really a backwards way of trying to deal with the lack of a carbon tax. So I think in the good scenario, the best possible scenario would be that something like that is instituted. And we're still going to have a significant increase in the carbon in the atmosphere. Temperatures are still going to rise, sea levels will rise. There will be, but it should be, I mean, the Dutch can manage, you know, with their probably a lot of dike companies will, there's a lot of opportunity in the dike business, I think. But I think if we take out action reasonably soon, we can avoid a calamitous outcome. If we only take action, say, towards the end of the century, then it's going to be extremely bad. I don't think people quite appreciate the fact that there's the momentum of the climate, of climate change. It's like even if you stop now, even if we immediately stopped all carbon production, the momentum will still carry forward and increase the temperature, raise water levels, make storms more powerful, all those things. So I'm trying to, like, what's the good outcome? Good outcome is we do a carbon tax, we minimize carbon production, we move to sustainable transportation, energy production, which, like I said, is going to be sort of solar, wind, geothermal, hydro, and some nuclear. I think we have to sort of accept that nuclear is a good option in certain places, and I actually think that the most likely outcome is a good one, or a reasonably good one where there's damage, but we recover. I actually think that will occur. So I'm quite optimistic about the future. I'm not suggesting complacency in the least, but I'm optimistic about the future.
I'm trying to find a woman. The lady at the back there.
Hi. Please excuse the pessimism of this question, but could we expend so much energy running around on the surface of the planet that we don't have enough to eventually get off it to another planet if we wanted to? And if so, how long might we have to that point?
I actually think as long as the sun is shining, we'll be fine. That's going to, if humanity had to get all of its energy from the sun, it could do so. It's really a truly astounding amount of energy that comes at us from the sun. I mean, it's interesting that if you took the land area used by nuclear plants, including the stay-out zones and everything, and said, okay, what generates more power, the nuclear power plant or just covering it with solar panels? In most cases, it's solar panels. Just the area used by the nuclear power plant in solar panels would generate more energy, because you actually have to have a big stay-out zone. You can't just put a nuclear power plant out in the suburbs and with a bunch of people around it. So you have to have this big clear zone, and so they use a lot of area. But just to give you just a sense of how much power can come from the sun, this is literally true what I've just said.
The gentleman with the red jumper there.
Hi, thanks very much for your talk. I think you're a visionary. So you talked earlier about setting up a sort of colony on Mars, and you've talked before about hopefully retiring onto Mars. My question is just why Mars, right? So people have talked about upper atmosphere of Venus or various moons. So like why?
Definitely not Venus.
Why? But like why Mars?
Oh.
So.
Oh, okay. So just by process of elimination, Mercury is obviously way too close to the sun. You definitely get. I mean, there's maybe some narrow habitable zone on the backside of Mercury, but I think one's sort of asking for trouble on that one. And then Venus, Venus should be a lesson for what Earth could become, in a worst-case scenario, which is sort of a superheated, high-pressure, in the case of Venus, acid bath. So it's literally a high-pressure, high-temperature acid bath. So definitely not a good place to make another. I think the most that any probe has even lasted on Venus is measured in hours. And then the Moon is close, but it's really a small rock, that's just circling Earth with no atmosphere. So very limited amounts of water ice that are sort of in very permanently shattered craters, and then it's got a 28-day rotational cycle, which isn't great for plants. it would be quite tough to make a self-sustaining civilization on the moon. So then coming to Mars, Mars is definitely a fixer-upper of a planet. You know, it's not perfect, but feasible. I mean, it's got a rotational period of 24.5 hours, so remarkably similar to Earth. It's got just under half Earth's gravity, so it's a lot closer gravitationally. It's got a lot of water ice. Almost all of Mars has water bound up in ice form in the soil. The soil has turned out to be non-toxic based on probes that we've sent there, so you could theoretically add, if you had a greenhouse and some fertilizer and you just sort of warm things up and pressurized it a little bit, then you could grow plants on Mars. And Mars has a CO2 atmosphere which plants like to consume. So plants consume CO2 and on net exude oxygen. So I think it's very, very doable to create a Mars base, self-sustaining Mars base, and then ultimately terraform the planet to make it like Earth, so we could just walk around outdoors. It'd be obviously a longer-term project, but it is within the realm of possibility. And then, of course, going beyond that, you're going to like Jupiter and gas giants, and you could potentially do something on the moons of Jupiter or Saturn, but that's way harder than Mars.
Alex Halliday, who is the head of maths, physics, and life sciences in Oxford, also a geophysicist.
So I loved your talk and look forward to talking more. NASA and ESA, and NASA in particular, has done a huge amount to transform our understanding of the solar system through wonderful planetary missions. The Apollo program, even though it had a political and military dimension to it, was persuaded at the late stages to actually bring some rocks back, which totally transformed our understanding of the inner solar system through those samples. So the way things are going with you, can you tell us how you envision private space exploration taking over from major space agencies and JPL and organizations like this in the future? With this move towards privatization, how are we going to be able to address scientific priorities as opposed to commercial priorities in solar system exploration?
Sure. I think space exploration is going to be a mixture of private and government activities, and in fact, for SpaceX, there are many things we want to do to enable scientific missions and enable NASA and JPL to be able to, and ESA and others to do much more for a given budget. In fact, we've had a number of conversations with JPL, which is located quite close to SpaceX, about using our Falcon rocket and Dragon spacecraft, because version 2 of the Dragon spacecraft will have propulsive landing capabilities. So version 2 of the Dragon spacecraft will be able to land on any liquid or solid surface in the solar system. So there's the potential to turn that into a generalized science instrument delivery platform for anywhere in the solar system. And then, if you conceivably, one could figure out how to do a sample return. If you were to land Dragon and have a smaller sort of sample return rocket housed within the Dragon spacecraft that could return some Martian regolith, that would be pretty cool. So we're exploring some ideas there, and I think we'll see at least some science missions being done in the future, maybe a lot of them. It's still at the early stage. But we do have we have Jason 3, which is a joint NASA ESA mission that's going to be launched on one of our rockets in about 2 years. And then, of course, we're flying the space station. So I think it's going to be a mixture of government and commercial. I'm for whatever means will make it happen. So I'm not, hard over on commercial or government. I'm just whatever works for all practical purposes.
Lillian Martin here.
Is it too early to think about establishing some, not rules, but some attitude toward the commons? Let it be common, because you know that the entrepreneurs are going to go and try to mine things there. There are many valuable minerals and things on Mars. And to keep it from being exploited, what kind of thinking do we have to do now?
Well, I don't think it's going to be economical to mine things on Mars and then transport them back to Earth, because the transport costs would overwhelm the value of whatever you mined. But I mean, there will likely be a lot of mining on Mars that's useful for a Mars base, but unlikely to be transferred back to Earth. I think the exchange of the economic exchange between, say, a Mars base and Earth would be mostly in the form of intellectual property. Anything that can be transmitted by a photon. I think that's the most likely exchange of things that will occur. Yeah, I mean, so I don't think we need to worry too much about sort of exploitation of Mars. Essentially, it's yeah. I mean, that would be a high-class problem to deal with. That's for sure.
Okay, lots of hands up the back. The gentleman with.
Hello. Just want to ask two quick questions real quick. We've been having a lot of argument about the food versus fuel debate. I just want to get your take on the use of biofuels as a means of transportation. And also, the use of electric cars is most likely to put some sort of strain on the electrical grid of our cities. I just want to ask what kind of adaptations you would like to see done to the transmission grid.
Sure. I'm not the biggest fan of biofuels because I think it's difficult. You know, again, I try to look at things like just calculate the basic physics of it. I mean, really elementary stuff, and say, okay, well, what percentage of the incident sunlight is bound up in usable chemical energy, and then once you have that chemical energy, how much of that is then translated into electricity? And you have to compare, of course, that total efficiency with just having solar panels. And I mean, unless I've made some really dumb mistake, which is possible, but you're about 100 times off with biofuels. I mean, at least 2 orders of magnitude. So essentially, what it boils down to is how many. What's your watts per square meter of electrical energy generated with the best case biofuel? I'm not talking about like take every assumption and maximize it. So don't worry. Don't say, oh well, maybe there's somebody could invent something better. Say, what is the best? Just envelope the whole thing, and say you had unbelievably efficient plants. Maximally efficient. I mean, you can't violate any laws of thermodynamics, but like assuming you're at the limit of the laws of thermodynamics in all those cases, and biofuels, at least for terrestrial, land-based biofuels, there's no way this makes sense. You end up being around maybe 0.2%, efficient, whereas in turning sunlight into electrical energy, whereas commercial solar panels are 20% efficient. So why would you ever do biofuels? And then it's not as though there are large swaths of arable land unused. So you have to say, well, if you go with biofuels, it's going to either result in wilderness being cultivated or an increase in food prices. And then you can also say, is it possible? If you stopped all food production in the world to generate enough energy to meet the world's needs, and you could probably, that's about right actually, if you stopped all food production. You could just about meet the world's energy needs. So now there is a possibility of ocean-based, because Earth's surface is mostly ocean. So if you could find a way to maybe some sort of ocean algae-based solution where you're unconstrained by surface area. Although I still think you'd have to compare that to a bunch of floating solar panels, and I think you still lose on floating solar panels. So I can't see how it would make sense. Sorry, what was the second question?
The
electricity grid.
Exactly.
At some point, there will need to be improvements to the electricity grid, but because there's a huge disparity in the peak energy use during the day and the energy use at night, and most charging of electric cars occurs at night, and we have quite a strong empirical basis for concluding this, because we can look at all of our customers and plot their energy usage, and it's very predominantly at night. It's just basically just like your cell phone. You go home, you plug it in, and it charges overnight. And there's the electricity grid has to be sized for the worst second of the worst day of the worst year, with some power plants not functioning. That's how electricity grid should be sized. Sometimes it doesn't work out that way, but and so most of the time you have huge amounts of excess capacity, and so in the US there was a study done. You always have this studies done on all sorts of things. Some are complete nonsense. I love the word studies say, but I think the study is actually probably accurate. That you could replace about 70% of the passenger miles in the United States, at least. I'm not sure how to apply to Britain, but 70% of the passenger miles with no changes to the grid, assuming charging occurred predominantly at night. And then if you combine that with increased use of solar panels on houses and businesses, so you have localized power generation. And the nice thing about solar power is it tends to match energy usage, because you're just generating power during the day and that's when you tend to use the most power. And particularly on summer days where you have air conditioning running. And air conditioning is a huge consumer of electricity. And you generally only need it when it's warm and sunny. So that's when you need it most. So I think we're okay on the grid front, at least for the near future. It's only going to become a problem once, let's say, electric vehicles are at least approaching 10% or 20% of the vehicles on the road. And then I think you'll be able to address the problem on a fairly localized basis.
I'm afraid that's all we have time for. I know many of you have your hands up. We will be running a blog, and we'll try and encourage Elon to engage when he has a second in his time as well. And clearly, lots of different things happening in the Oxford Martin School around this that we'd like to engage you all in as well. I'm going to ask the Vice-Chancellor to make some concluding comments.
Ladies and gentlemen, it's worth remembering that the great breakthroughs in exploration of the world in past centuries came from this combination that's been touched upon in the question time of government sponsorship but private genius and drive. And it was pioneers that discovered the Indies, that crossed the Atlantic, that explored the western extremes of Canada and the United States. And I think you'll agree with me today that we have heard this evening a true pioneer. And as we imagine the possibilities of space exploration, we've heard tonight some of the possible solutions that might take us there. Like Ian Goldin, I had the great pleasure to visit Elon at SpaceX in Los Angeles. It's hard to describe the scale of the ambition, the scale of the enterprise as the rockets are being built. You see not only a real focus and dedication on solving practical problems in this vast, many football field size factory, not only rockets being built, but also soaring ambition in the new designs, the carrying of astronauts, as we've heard, trying to turn the rockets into reusable vehicles. And I think today we've really had an insight into the way Elon's mind works. And I think it's given us all an object lesson in innovation. And you know, don't limit your ambitions. Go back to first principles. Be ready to make lots of mistakes, but not so many that you run out of money.
Right. Exactly.
And perhaps the last and most important of all, don't buy ICBMs from the Russians.
Right.
Ladies and gentlemen, it's been a fascinating lecture, a fascinating question and answer session. Let me thank all of you for participating in it so wonderfully. But most importantly, would you join me in thanking Elon Musk for coming to Oxford, for visiting us, and for giving us such a wonderful exposition this evening.